I know softball was out. So I'm missing a couple here too because softball's out. So, all right. Anybody do vinyl records? Anybody into vinyl records? Anybody seen an old turntable? Okay, I've got some people that have seen an old turntable. I didn't realize it until my husband, of course, is a musician, and he's a jazz musician, and we have been babying a turntable for years and years and years, and we move it. And it was like, he says, well, if you want to demonstrate, speed and frequency and all of that, the markers on the side of the turntable will do it. And I went, oh, really? I didn't know that. It's one of those, I didn't know that kind of things. So I did find a YouTube about the markers on the strobe on the side of the turntable. And that actually, when you are trying to set up the timing on your turntable, there are actually, depending on your turntable, there are actually like 4 different markers to set your 33 1/3, or your 45, or your 70. You want to turn the lights off? And it really is to help you adjust the timing on your turntable. This one happens to be a Techniques. This one's very similar to the one my husband has. But if you get the strobe, setting up the strobe, it will help you set up and adjust your turntable. And what you're doing with the strobe is you're setting up the timing to actually adjust the revolutions per minute. And if we're talking simple harmonic motion, revolutions per minute are going to be associated with your frequency and your period on your turntable. So in case those of you who've looked at high-end turntables want to know what those things are, that's exactly what those things are. The other interesting thing about it is we were talking about, I was listening to some interesting little tidbits, and if you're into rap, hip-hop, or other music, since we're talking about sound, there's this idea of sampling. And the sampling is, depending on how they did it, if you're into techno music, they actually would use a turntable, and they would use a piece of vinyl on top of the vinyl to cover the rest of the track, so as they're spinning it around, they're only getting whatever's over the exposed portion of the track. Apparently, the first evidence of sampling on popular music, which I did not know about when I was listening to the radio yesterday, is on the Beatles' Sgt. Pepper's Lonely Hearts Club Band with the Calliope, and they actually took tape of the Calliope and threw it up, or cut it up into little bits and pieces, and pulled it back out, and actually spliced the tape back together, physically spliced the tape back together for the Calliope sound on that particular album. So it's kind of interesting that we end up playing with physics, and we go, okay, didn't know that was there. This is, oh, come on, did I not? Let's see if this is the right one. Oh, this is the comparison of simple harmonic motion to this one's a good one. Let's see, we get the sound on this one. I'm going to pause it here. Okay, let me go here. We're going to get this one up. Okay, are you guys hearing that over there in Tonkawa?
Yes.
Okay, cool.
Let's take a look at this turntable of a record player. I've placed a yellow marker cap on it so we can observe the circular motion of the cap. Does everybody see that the cap is moving in circular motion? Yeah. Okay, now let me add a side view of the turntable and yellow marker cap. Do you see how the cap appears to move in simple harmonic motion? Yeah. Okay, so I will add a vertical mass spring system moving in simple harmonic
So that's a little bit more fun than the one I showed with just the demonstration. So that one is in there. And this one is it. This is the one that starts looking at how things are correlated and how we get the motions that we can apply. And this one is done. Yeah, okay, let me see if it's interesting. I got a lot of interesting sound in here, but
I should probably polish them because I've been using them all that. Okay, here is a soup bowl that I slightly borrowed from a cafeteria in Cambridge. And I got a few bowls, let's say three, and swirl. You see that the bowls circulate in the direction that I'm swirling. Of course, you say. Now, when I say swirl, I mean do this motion. I'm not actually rotating the whole thing, I'm just doing this. Okay, so when I swirl, those balls circulate in the direction that I'm swirling. I'm swirling in this direction and balls circulate in the same direction, that is counterclockwise. Now, let's increase the number of balls, make that more crowded. When I swirl now, balls start circulating in the wrong direction, opposite direction. So, transition. With one ball, the circulation is the same direction as swirl. 2, 3, what I've already seen, they circulate in the same direction. 4, it's still the same direction, but 5, there's a lot of hesitation. 6, but at 7, it's pretty clear that they are circulating in the opposite direction. And 8, and so on. This is quite remarkable, and it's a bit like a phase transition, if you like, a phase transition between gas and liquid. When you have only a few of those balls, and I swirl, these balls are independent particles. They don't talk to one another. They are minding their own businesses. And what happens is that whenever the wall of the soup bowl bangs against one of them, it just transmits the linear momentum in the same direction. So if I'm swirling like that, they are being sent in the same direction. That's why they circulate in the same direction that I'm swirling. Because they are not talking to one another, they are independent particles. In contrast, when you increase the crowdedness, well, whatever linear momentum I input into the system gets scattered among the neighboring contacts because they're very closely touching one another. But what doesn't get wasted is the rubbing effect. So imagine that you have a ball like this, and then the wall of the soup bowl rubs against this. Not only does it get pushed away, but it also gets rotated like that. And this rotation is transmitted because the neighbors are very close to the next one, the next one, the next one. So this rotation is propagated among all the entire group. So the linear momentum is being wasted, but the angular momentum, that is the tendency to keep rotating, that's the quantity that measures how much there is rotation, gets transmitted. So you have a transition from the linear momentum dominated regime to the angular momentum dominated regime. And what happens is that when you rub it like this, it rolls in the direction opposite. It starts moving, slowly drifting in the direction opposite to the way I push. That's why there is this takeover effect. And that is really a little bit like, in some facetious fashion, like a transition between gas and condensing to liquid. Because you see, in gas, molecules are just flying around minding their own businesses. They're free and they don't really talk to one another, and they bounce against the wall of the vessel and then they bounce. But when you are a liquid, you have molecules that are touching against each other. They can slide against each other, but they interact a lot. So it is really like a transition from gas to liquid. And the order factor is increasing the crowdedness, is like lowering the temperature, increasing the pressure. And if you keep making them more crowded, then they eventually freeze solid. So you see phase transition. Now,
so that's one example of how some of the stuff that we do can be modeled into something else. And that's why we look at these simple harmonic motion, we look at angular momentum, and then we start extrapolating it down to more dedicated systems because then we can approximate and see what's happening on an atomic level or an atomic scale, and try to explain physical phenomena using models. And that's why we do these kinds of things. And I talked to you guys about resonance and dealing with the bowling balls. Well, I found it. If you guys haven't seen this one, it's been circulated on YouTube, and they set the bowling balls off at the same time. And they actually will resonate and then take each other out of phase and in phase and bring themselves back. Because there is a bit of communication through the rod that's holding them together. And we also see the dampening, of course. So when we're dealing with pendulums, that's one of the things that we have to worry about is dampening. So it's a dampened simple harmonic motion system rather than an infinite one. But now you can see the resonance coming back in, just like we were talking about beats before. And you'll see different patterns as they start to resonate out. So I've given you all of those. So you have those to kind of look at and play with and have some fun with. I had one person send me some simple, or for the Doppler effect, that was kind of an intriguing one. Didn't have a photograph that went with it. It was more a description, and it was related to a cannon. But the problem with the audio and the visual of the cannon doesn't necessarily show the Doppler effect. However, if I'm flying on an airplane, and that was the description that was provided, and I'm sending off bullets at a certain time period as the plane is getting closer and I'm aiming towards the target, it would appear that those bullets are coming at a faster frequency as I'm getting closer. And if I'm still aiming at that target as I pass away, because of the motion of the plane, the bullets are going to be further spaced out. So it was a nice description of the Doppler effect, just that the sound didn't quite go with the Doppler effect. So now I'm going to go to the ones that people had submitted. And I've got Doppler effect and simple harmonic motion in the same file. So my favorite was Trenton's. Let me see if I can find Trenton's. It must be this one for simple harmonic motion. There it is. This is the one that triggered my memory on the bowl problem, because I can, as the ball goes back and forth in the bowl, it demonstrates simple harmonic motion. It's almost like a pendulum without a string. So that's where, and that triggered my memory there. But this is Trenton's. I thought this was the best one with the pendulum, and the star is not the pendulum. It gave me a good chuckle. Obviously, the cat did not care. The cat did not care. I don't know if you guys are on Facebook, the best trend right now is it's a meme that's circulating that says if your pet was on a dating site, take a picture of your pet and move it along. I think they're hysterical. They are totally hysterical. So that one's kind of fun right now. Let's see. What else did I have for simple harmonic motion? I had a couple of these type. These are good examples of dampened simple harmonic motion, where you get the vibration of the end of a plank or a piece of metal. I think I have another one in here. That file is so empty. I thought I had another one. So that's another one that's there. Let's see. Okay. Bouncing up and down. So we had different pieces on that one. Oh, let's see if I had another one. Swings. Good old pendulums on swings. Had a couple of those. And here's another swing. back and forth. So we've got lots of different pieces there. Doppler effect. No, I'm not sure if we can get the sound out of this one. Not quite getting the sound, but it's a normal demonstration of a Doppler effect. This is more on the line of that one. I've seen it done with drain pipes. I've seen it done this way. I've seen it done a variety of different ways that you can get that Doppler effect to get it demonstrated. I'm not sure which one is the better one. I think this one you can hear the geese or the ducks. And I'll post these so you guys can play them on better speakers. But where's yours, Leo? I think this is yours. So did the policeman stop?
Yeah, he turned around and right here in the parking lot in front. Pulled up.
Two of them.
They made me get out of the car and they flashed it. They thought it was some kind of code for.
Oh.
Yeah, that was scary.
Well, this is the second time that I've known that the policemen have stopped doing one of my.
They made me pull out my computer to show them.
The other one that I had was when we do the pinhole camera. The guys were out setting up to do the pinhole camera, and we're using a street light, and they were setting it up there, and they had used an Altoids can for their pinhole camera, and this is when we still could get film developed pretty easily. And the policeman came over and said, "What are you guys doing?" They tried to explain, "I'm doing this pinhole camera." And the policeman opened up their camera and flashed the flashlight on it. And it was like, what? They sit there and they go, surely nobody's doing some strange physics experiment, right? And they're going, this, and then it's the actual truth. So sorry about that. Sorry about that. But that's the second time I've heard somebody, but the other one was on a pinhole camera, and you're going, what on earth? And here's a creative aspect. I like these two. Instead of the horn, just using the lovely throaty roar of the vehicle. And we've got the throaty roar of a good motorcycle. And then somebody got the NASCAR clip. Where's my NASCAR clip? There it is. So you do get it at NASCAR, you do get it at Formula One racing, you do get it in a variety of ones, but here's one that they actually use it for. And looking at a fetal heartbeat, for using Doppler for a fetal heartbeat. So you guys did pretty good. Looking at the different Doppler effects and looking at the different simple harmonic motion and looking at a variety of different things. So I always love doing it just to get the different aspects to it, because we see it in real life all the time. I'm a little surprised nobody did simple harmonic motion looking at a tire going around, because your valve stem on the tire is another form of simple harmonic motion, or the letters on the tire are another one. I've had bicycle wheels done for simple harmonic motion. Turntables, as you saw, are another piece. So we have simple harmonic motion in a variety of different aspects that we look at. So good job, guys. I will get grades posted on there, but I wanted you guys to see what you all had turned in so that we are looking at things. I don't know if they have talked to you about the pinhole camera one. So something to start thinking about. The large project that we will be doing at the end of the semester for your lab is a pinhole camera. And one of the things associated with the pinhole camera is that it does take a little bit of time in order to get the images that you're looking at. I think I talked about it already, didn't I? Kind of gave you a heads up. There's lots of different websites and things that you guys can use to find how to do pinhole cameras. But let's see, you guys see me, or do you see the computer still over in Tonkawa? Just black. Okay. I always have trouble getting the. Ooh, that's weird. Ooh, that's not good. Well, we'll just go to the document cam and go from there. Maybe. Okay, I got the document cam. Okay, you see the document camera? Okay, cool. See the document camera. All right. So looking at the homework, I saw that the one problem that people seemed to, it seemed to be the one that had the most difficulty with. Let me get my stuff set up. Most difficulty with was the acceleration on Mars and doing the simple pendulum. So if I have my simple pendulum, let me get my simple pendulum. If I have my simple pendulum set up, and this is one that you're likely to see an exam problem on. There's a good example in the text. You're likely to see an exam problem on it. And we've got the force due to gravity is coming down, and because it's tied to a string, it's going to go down that direction. And we went through the derivation, and the period of the pendulum is 2 pi times the square root of L over G. And you're likely to see a problem that says something like this, that we put good old Neil Armstrong on the moon, and he pulls out his pendulum and his pendulum has a length of 1 meter because you can put your string in your pocket. And he sets it up, and he's going to watch it, and he's going to let it go back and forth. And when you're counting, and he'll say that it makes 5 complete cycles. And somebody better have a calculator out for me because I did not bring my calculator this morning. 5 complete cycles in 10 seconds. So I need my period of a cycle, right? So if I do 5 complete cycles, so the frequency is going to be the number of cycles per unit time. So we did 5 cycles in 10 seconds, so I'm 1 over second, so I'm in hertz, so I'm at 0.5 hertz. And period is 1 over the frequency. So I'm going to go 1 over 0.5 hertz. And this, if we do our math right, this becomes 2 seconds. So my period is 2 seconds. And if I know that, so if I'm trying to find this acceleration due to gravity on my foreign planet, first thing I got to do is multiply by both sides I got to square both sides, so I get t squared is equal to 4 pi squared L over G. Put G over on this side, and I get 4 pi squared L divided by t squared. And now I get 4 pi squared, and if we use a 1 meter long pendulum, and now I do my 2 seconds squared, I get the right units, meters per second squared. This is going to be 2 pi squared, and that's what? 6, well, whatever pi squared. Give me the value for that. 19.73. So this is 19.73 meters per second squared. So that's not on the moon, it's on a pretty heavy planet, because remember that we also know that if I use my Newtonian G m r squared, this is G m, which is the mass of my planet, divided by r squared of the planet. That equates to my acceleration due to gravity. So we have some idea that either I've got something that's affected with the radius, or I have something that's affected with the mass that's going to make it different than being on Earth. So we can actually go back and look at it. And the way your problem was written is that we went to Mars and we found that the acceleration, was 3.7 meters per second squared, and that's on Mars. And on Earth, we've been using 9.81 or 9.8 meters per second squared. So that's what we've been doing. And it says, what length of the pendulum has a period of 1.2 seconds on Earth? What's the length of the pendulum? So if I've got t is equal to 2 pi square root of L over G, or I've got t squared is equal to 4 pi squared L over G, and I want to find Earth, I'm going to do t squared G divided by 4 pi squared is going to give me my L. So all I've got to do is plug in whatever G that would be. And if I'm looking for, if I do it for Earth, I have to plug in the Earth value. If I'm looking for Mars, I have to plug in the Mars value. And I'm guessing one of the issues is you probably left it in meters and you went and typed it in WebAssign and went, uh-oh, I got an because WebAssign wanted it in centimeters. So that was possible why a lot of you missed it on the first time around. Then it was looking for the object has a mass and spring constant, and remember we could go back to our spring equation and look at how that was related to omega is equal to 2 pi times the frequency is equal to our spring constant k divided by the mass. And now if you know the frequency, because we can go back, if we can get period, we can get frequency. And if I'm given the spring constant, I can calculate the mass. And a lot of times it's just remembering that portion of the situation. Okay? A lot of times it's just remembering that. And I didn't see too many problems on the sound homework. Or at least nothing popped up that there was any real big difficulty on the sound homework. So let's talk about what to expect or plan for on the test. So test is going to be next Wednesday, and we're covering simple harmonic motion and sound. So some things that you're going to want to know. It's going to be a mix of some conceptual questions and some actually plug in, do the calculation questions. Things that you definitely want to look at. You want to be able to identify the period, the frequency, the amplitude on the wave, okay, and wavelength, frequency, amplitude, and wavelength. You're going to want to be able, if I give you, so just identifying that this is the amplitude, identifying that this would be the period if I'm with respect to time, identifying that this would be the wavelength if it's respect to distance, and that the period is 1 over the frequency, or the frequency is equal to 1 over the period. So that's one of the things that you'll want to be able to do. You'll want to, if I actually give you numbers, you'll want to be able to write the wave equation and be able to plug in for omega. And remember that omega is 2 pi times the frequency. So that's one of the things that you're going to want to be able to do. Or if I give you the wave equation, be able to pull out that information. Because those were some of the problems that we did, and that was one of the things that I asked you to do on your simple harmonic motion examples. be able to do that part. You want to be able to tell me the difference between a transverse wave and a longitudinal wave. And remember, my longitudinal wave was more like a slinky. So you'll want to be able to do that. Tell me what the difference is. You'll want to be able to calculate the speed of the wave. And that's the wavelength times the frequency. And if I give you an echo problem, remember that if I'm doing an echo problem, and this is the cliff, that the echo has to come forward and back. So you'll have to remember that I got to deal with the distance aspect of the problem. You'll want to be able to use Hooke's law to calculate spring constant. And you may want to refresh yourself about the energy. If I'm trying to calculate the velocity at the top or the velocity at the bottom or the velocity in the center, remember that the potential energy of the spring is 1/2 kx squared. And we had a couple of homework problems on that, even though it seems like a long time ago. We've had a couple of homework problems on that, looking at the spring part. And we did it, also kind of applied that to, I'll leave that under there so I don't mark up the paper. And I think you even have a problem that sort of looked like this. We have our little spring hopper problem. It gives you K, it gives you the mass, and we let it go up and it comes back down. And we actually can calculate the height. How high did it go? Because remember that the potential energy of the spring at the bottom ends up being, and we know the potential energy of the spring at the top. So this is going to be 1/2 kx squared is equal to mgh. And if I know k and I know h, or if I know k and I know m, and I'm given the energy, we can figure out how high it goes. So we did problems like that. Remember in the sound part, we've got the different pieces. So conceptually, so from some concept things, you want to know what beats are, what pitch is, what timbre is. You'll want to do a pendulum problem because you're likely to see a pendulum problem on the exam. You're likely to see my pitch. There will be a Doppler problem. So you'll have a pendulum problem, a Doppler problem. You'll have some conceptual stuff associated with that aspect. The other thing on the sound, you'll want to be able to calculate decibels if I'm giving you an intensity. And if we have multiple items, the increase in decibels. And you're likely to have a concept question about sound in general, talking about human hearing and ranges of things. So that you're likely to have some concept questions along those lines. You get an 8.5 by 11 piece with anything you want written on it. But I think that kind of gets us where we're at. We start Friday. Next Friday we'll start with electricity. And I think you had your kind of pre-work for electricity was due today. And I'll probably get the electricity homework posted shortly so that you guys can start on it if you want to and get ahead of things. Questions? You guys good over there? You're in the dark over there in Tonkawa, so I can't really see you. Any questions? Alrighty. If you got a question or something, email me, and I'll try to respond to it before the exam on Wednesday. Did you guys measure the speed of sound this week over here? Yeah, you did? In the tube? Had it come out good? No? The computer was being weird? Usually the big mistake is forgetting to measure inside the tube, because if you've used the FedEx tubes, there's a lip inside, and so your distance isn't the outside of the tube, it's the inside of the tube. And so that's one place that you're going to get error. The other place that you get error is you forget to multiply by 2, because it's the sound to and from back. And the other source of error is pulling it off, making sure you're at the exact same spot in the pattern on the screenshot. Because and having a good snap, somebody who has a good snap, because if you've got a fuzzy snap, that pattern just looks bleh. Alrighty, guys, we'll see you all next week. We could start electricity, but